All right, whenever you're ready.
Yeah. Yeah, quiet in the classroom, guys. Yeah. I guess, is it better for people if I just try to run through the entire course?
Yeah, all of that sounds good.
Okay.
We're here for two.
Yeah, this will take a minute. Okay, I guess I'll start with, do people know the two types of harm?
Allocative and representative.
No.
Yeah, representation.
Not got to that yet.
So, the first kind of harm would come from if you're using your model to try to allocate some kind of scarce resource. So you can have some kind of model that allocates more to a specific group, and that would obviously cause harm to the group that is underrepresented. And the other type would be representational harm. So that would be more so like, if you have your COMPAS model and you predict that African Americans are more likely to commit a crime, those people will then be further policed, which in turn will produce further features that make them look bad, like higher arrest rates and stuff, which then makes them get further policed. And
There's like a
exactly,
feedback loop.
loop there.
Historical data.
Can I ask a question about that? What would be like like a university admission? Is that like allocative or representational?
Sorry,
If there's
what'd
like
you say?
if there's like limited slots for like a university program, is that like allocative or like
Brother, you know the
representational?
answer to that.
I don't.
What is that allocative?
Yeah,
Okay.
that's
Class.
Yeah. Okay, so then the main idea, like for moving forwards, for how we actually make sure our model's fair is that fairness is a constraint. So if you have like the best model possible, that model could be fair or unfair, but to increase fairness, you have to reduce the performance of the model, because the best model you can obtain has no constraints on it. Any constraint that you apply to it is there's some trade-off. You can increase the amount of people you accept from one group, but to do that, you will have to lose accuracy for another group. So the main idea there is like fairness is a constraint that you apply on models, and you'll see that through the loss functions later on in like the later chapters. And another key idea is that there's like different ways that we can think of fairness. So there's three main fairness metrics that we use. Does anyone know them off rip?
It starts with C. Calibration and sufficiency.
So those are kind of like in the same category. So like three main fairness metrics that we're looking at. Yo, Ed, you got it?
Equalize, like loss rate, or like equalize.
Yeah, so equalized odds, so separation, independence / statistical parity, and sufficiency, and calibration is kind of like a subset of sufficiency. So those are our three different ways that we try to make a model fair. But the problem is you can't have these different fairness metrics at the same time unless there's like very specific criteria that are met. Yeah, so the first one, independence, is basically just the thing that you're trying to equalize between groups is just your probability of acceptance. So that is basically saying like, and for each of these like things that I'm writing out, it's the thing you're trying to equalize across different groups. So if I have group A and I've got group B, independence is basically saying you want this probability of, like, let's say this is acceptance into a program. If you have in your first group that like 30% are accepted, independence would say that in group B you also have to accept 30% of them. So for the next one, that would be separation or equalized odds. So that one has like a mathematical form that's kind of like this equals 1 given actual y is equal to 0, and the other one, so this is like your true positive rate and your false positive rate. So what you're trying to equalize there, you want to equalize both of them across different groups, and so that's meaning that you are equally wrong for both of the different groups, and you're wrong in the same manner. So the reason why that is important because let's say for group A, their like false positive rate is like 5, and false negative rate is 0, and for the other one, you've got the inverse. So depending on whether or not being classified as positive is a good thing, let's say it is. So this group A, they like have 5% like false positive rate, and this group B is 5% false negative rate. So that means in group A, if it's getting accepted into college, you're 5% like more likely kind of thing to be accepted even though you shouldn't have been. And for group B, you're 5% more likely to have been denied even though you shouldn't have been. So that's why you're trying to equalize both of them at the same time. You're trying to get both of these to be like 2.5 and 2.5, you know? Because that's considered more fair because you're wrong in the same way. And so that's kind of looking at like when you would like use these two different things. This first one is kind of more relevant for like an allocative kind of issue where you're like, you want to make sure you're giving the same amount of things to these two different groups. Whereas when this one's more relevant if a particular thing, positive or negative, has like a big positive or negative effect. You'd want to equalize that across the same way, just because obviously it's unfair to overly predict crime if they don't actually predict crime. And then for the last one, sufficiency, this one's probably the most confusing, especially the difference between in and calibration. So sufficiency says that your probability of predicting a certain thing given a risk score, which is equal to little r. So for sufficiency, you want to equalize this across groups. So a way of thinking about that, if the actual base rate in a population is 20% for two different things, if you then predicted on group A, you predicted like 25, and then here you predicted 30, this would not be sufficient because given a certain risk score, you get like a different predicted probability. So basically, it doesn't mean the same thing for both groups. So here, like, if the actual base rate is 20% and you're predicting it's 30% versus 20% and 25%, so the actual base rate doesn't mean the same thing in the sense where if, like here it's 30, that would be sufficient because for both of them, it's wrong, but it's wrong by the same amount in the same direction. So sufficiency is kind of like the idea of that what this score means the same thing for both groups. Like if it's 50% more, it should mean 50% more for both groups. Like if it's dead on for one like this, that doesn't mean the same thing for both groups because here you might say, oh, this person from group A is 20% likely to commit X crime, and this person is 30% likely to commit a crime, even though they're both 20%, so not sufficient. If it was, you're predicting, oh, you're saying 30, but both of them are 20% likely, that is sufficient because you're treating them the same way based off that score. Does that
But
make
it's
sense?
not calibrated?
Not calibrated yet in this case because for calibration, you need to add another thing where you say this is all equal to little r, which is just saying the probability you predict matches the base rate as well.
Okay.
So they both have to be 20 then?
Yeah,
So
yeah.
if
So
they're-
then
yeah,
for it to be calibrated, this would both have to be 20.
So
And this
if
is
it's the same number-
specifically calibration by group. She puts in the slides that she just calls this calibration. It's calibration by group. You can like in the textbook, that's what it calls it. Because if this was here, if group A was like 99% of the population, group B was like 1%. If you predicted 20 and then here you predicted 30, your model would look calibrated. Your model is calibrated on average, but it's not calibrated by group because for each group it's not calibrated. So your model can generally be calibrated without being calibrated by group. Does that all make sense?
What was the second term? Like not the explanation, but just the term.
Like calibration by group?
Like the middle, like the PY equals that.
That
What is
one?
what is the
Uh,
term?
That one is
Equalize.
separation, right?
Yeah.
Yeah.
Okay.
Or equalized
Those are the
So
same
what's,
thing.
what's the
Yeah.
one under the sufficiency?
Yeah, this is sufficiency. You add this equals R part, you get calibration.
What's the R? What's the big R?
Big R is just a variable to say any risk group, or any risk score, sorry, and little r is a particular risk score. So it's just saying like, this could be like 20%. R is equal to 20%, you know? Yeah,
If we're doing by group, we need to add the A thing in the.
yeah, yes. Technically, when it's by group, you also add a third variable, A is equal to A, to say that you're equalizing it by each group. That doesn't matter, that's but true.
And what does risk score mean?
Um,
Probability?
Yeah, risk score varies depending on context, but it's kind of just the odds of an event occurring instead of specific classifying. Like for the Compass ones, it's the odds that they would commit another crime. For like loans, it would be the odd that they default on a loan. That would be their risk score, because you don't know when you give the loan whether or not they're going to default. But you can say this person's like 25% chance of not repaying it. That would be the risk score.
So the why is the thing happening, and then the risk score is.
Sorry.
The why is like.
Oh, the
thing
Y
that's
is like the
happening?
actual
Like,
like prediction kind of. Yeah, I see what you're saying. There is no actual prediction. I don't know, that's just how
That's
it's
like the
written
model
there.
saying it's gonna happen,
Yeah.
Right.
like 0 or 1.
Yeah.
Okay. So that is kind of lecture 1 in a nutshell.
Let's go.
Oh yeah.
You should run your own lecture at the same time, and we can.
Just talk louder than
Okay, so for lecture 2, that's mostly focusing on biases. So the first thing that they get into is the idea of resampling versus reweighting. Does anyone know what those are? All right. I get how it feels like to be a prof, man. You just ask a question, you look around, you're like, nope.
At least there's people here.
Yeah, go for it.
Okay, resample, you just add like.
Yeah,
you
like-
increase the frequency of how much one group occurs. So if something's unrepresentative against a lower population, you just like you can maybe double it. That's for one example of resampling. For reweighting, you just like it's like a multiplier you add onto like that specific group. So then like you have more contribution to the model. Does that make sense?
Yeah, so with resampling, like you said, there's 2 types of resampling. So you're basically, the reason why you'd want to resample or reweight is because you have your 2 groups and one of them is overrepresented, and the other one would be underrepresented in the data, right? So you got like 80% like men, 20% women, but you know in the general population it's 50-50. You're going to want to do something about that because otherwise your data is clearly biased towards man. So the one way you might do that is by resampling, and there's 2 ways you can resample. So for the first one, you oversample, and the way you do that is you just duplicate somebody's woman. You just add them back into it. The issue that comes with that is that you might have, for some of these women, they might be outliers, or they might have like very particular set of features, and then you could get overfitting on them because they're duplicated many times in the data set, even if they're not representative of women at large. Alternatively, you can undersample. So I've got my 80% men, I can drop a bunch of them for the data set until it's closer to equalized odds. The issue with that is now you've just thrown away a bunch of data that is probably useful for your model. And the issue with both of these approaches is that people without a statistical background just really don't like if you fuck with the data. Like they don't get that you can like just duplicate people. It's just not appreciated for that reason. So something you might alternatively do that's basically the same thing as oversampling is you might reweight it. So the way reweighting works is you choose samples that are from your like less privileged group, and you will adjust your loss function so that it places greater penalty on getting them wrong. And from there, like your loss function will correct more if it predicts wrong on something from your less common group. And really, I don't get how this is functionally different from oversampling, but that's the difference between them. So, any questions with that? No? Okay.
Sorry, could you just repeat that last thing? They adjust the loss function
Yeah.
to give a greater penalty?
Yeah, so let's say if it was a man that you got wrong, you would just like keep your loss function as is, so it'd just be like loss, I'm just gonna say it's like X would just like go into the model. But then if it was a woman, you might say like, oh, I'm just gonna multiply that by 2. It just to give it a greater impact anytime like a woman was predicted wrong.
And what you were saying about like how you don't understand between the oversampling is like that's pretty much the same thing.
As
It's
just having 2 women
duplicating
in
the
your group,
women.
yeah.
in-
I don't know
yeah.
how it's different. I'm sure there's some reason why they're different.
Yeah.
It looks the same to me.
Okay.
So is there a reason to use one over the other?
People don't like using like the oversampling, the undersampling, because from outside, like if you are just a decision maker, you don't really know much about AI, and you see that they're like, wait, we have like 2 Mary Janes in our data set. They just don't like that.
Oh, okay.
Like that was the reason she gave in the lecture. She was like, people don't like it when you touch the data directly.
Okay.
'Cause people aren't very smart. Like, I don't know. Yeah, so the next thing that could be in the bias section is data imputation and the issues with that. So data imputation is where you add in values to account for missing values. And the common ways that you might do that is you might take like the mean or the median, and you just stick that in for the missing values. But this can result in bias because the mean or the median value may not be representative for this smaller group. So I guess like top of head, like an example that could be would be like if you had a data set that was mostly like white people and it was like something with like skin diseases and you imputed for using the like median melanin like value in their skin. If you did that on a person who was missing that value and they were like African American or Asian or something, like clearly that value is not going to be representative of theirs, but you just stick that in there because that's common practice, so that's not good. And the way you can identify if data has been heavily imputed is if you look at the distribution of all the data and like all the buckets, they kind of look like this. Then you got one that looks like this. Like clearly just filled in a bunch of that. So that's something that you can look out for when you're pre-processing your data set. You look for whether or not they've imputed it with the median value. Yeah.
Yeah, is data imputation related to like creating new samples, or is it only for like filling in missing like variables?
I think it's more so for like filling in just like the missing values.
Okay.
So next, there's the 3 types of encodings for categorical variables. So those are the like one hot, and there's the target variable, and there is the ordinal. So one hot encoding is the same encoding that we've all been using for categorical variables. You just substitute each category is with like a 1 and a 0, you know, based off what it is. For target variable encoding, what you do instead is you look at what the categorical variable is and how it relates to the actual label. And then based off how common that categorical variable is based off the label, you then average it and you get that average value. So like if you had like, it's hard to think of examples, but if you had like x1 never shows up, x1, x2, and x3 are going to be categorical variables. If you have x1 and it never shows up when the prediction should be 1, then like x1 would be encoded as 0. If a third of the time x2 was there when it was actually predicted as 1, you would replace all those with like 1/3. And then if x3 was always there, then you would replace that with like a 1. I feel like that's not the easiest way to understand it, just like that. Like, who doesn't get it, I guess?
I don't really
Like,
get
I
that.
think
Yeah,
just
let me
start
try,
from
think
the
different way.
beginning of that.
Yeah, so like, I'm trying to think, it's easier if I can think of an actual example. Let's say what you're trying to predict whether or not the food is a taco, okay? And you have a list of like ingredients as your categorical variables. Ingredient 1 is apple slices, I guess. So if you look at all of the data you have, anytime like you have apple slices, it's never a taco. So you take that like average value and you say x1 is equal to 0. If this is, what's something that's like in tacos?
Guacamole.
Yeah, sure. And so like 1/3 of the time your tacos have guacamole, so it will end up being that. And then this one's like fucking, yeah, like cheese or taco shell, like it's always there. So that's kind of how that's done. And then for ordinal encoding, you encode it with like numbers like 0, 1, 2, 3, assuming that you have some information about what the order of the value should be. So the way that you have issues with these different encodings is if, for example, you have a whole bunch of, let's say you're trying to like predict if somebody should get a job or not. And in your data set, in the main group of people, like there's a whole bunch of people and they've got their bachelors and their masters. So you'd see a whole bunch of like those categorical encodings. Like, so you have like a whole bunch of bachelors and you got like a whole bunch of people who got their masters. But then the issue is some group of people who may like always get their PhDs, for example, they would look like this, but they're never represented in the data. Like you say, like there's like 2 of them, you know? So when your model goes to predict who should like get the job or get a promotion or something, it goes and sees like, oh, well, a lot of the time people who get their masters get promotions, so I'm gonna like predict that. But what it misses is like the 2 people of your thousands of people in your data set who had PhDs always got it. But since it only happened like twice, your model doesn't think that's very important, so it discards it. So that's kind of the issue with the one hot encoding with that. Just for very small groups, if it's very common for that category to be in the small group, it might get lost because the model might think it's not important for predicting. The issue with the target variable encoding is the way she told it was that you want to do these averages across your entire data set and that's going to leak into the test set. That seems crazy to me. I don't know why you wouldn't just average with just the training set. But she said apparently this will leak data from your testing set.
What's the advantage of target variable then?
It
The-
weights, like,
You can like
Shit more,
organize it based on like how often it happens.
Yeah, yeah,
It's
like
like-
you're
yeah.
getting more information from this than in this case. Because in this case, an apple looks the same as guacamole. In this case, an apple is clearly less related.
Okay.
Even if there's 5 apples,
Yeah.
guacamole.
But isn't it leaking information? The target variable is the
Dude,
only
what
one that
is
actually
it?
looks at the result of it. So like, aren't you giving your like, are you putting in this information that already knows the result of it? Is that not what it means by leaking?
Yeah, I mean,
Okay.
Straight data leaking. Memorize.
Write that shit down.
leaks data into the training or the testing set.
Sorry?
So let's say you only have two PhDs,
Yeah.
the whole data set, would it not still be a
I'm just
small
gonna write that
number
on
in
there
your
as an
target
extra
variable?
font. I think it's,
Yeah, target variable is not the way to fix it. You want to fix it with
Okay.
ordinal. Yeah. Yeah, so ordinal is the one that fixes this because if we had this being like, here you got like this like a high school diploma, and you get like your, you got your BSc, MES,
Wait.
PhD. So if you rank it like this way, where you know the relationship between it, even if you don't have like a lot of PhD holders or like high school graduates in your data set, the model inherently knows that if you get like a 1, like you have a lot of bachelors, they're less likely to get it. But if you got like a 2, like those people were more likely to get a raise, which in 2 is high 1. So then if you got a 3, like, oh man, you're like the shit. So, but the downside with ordinal encoding is obviously if there is no inherent order between the things, then it'll just fuck up your model. If like instead this was the ingredients, there's no order to ingredients, so it doesn't help you.
Very ethical guy.
Yeah, so then the next thing from this chapter was the idea of proxies.
Just learned.
Yeah. So proxies are just essentially, there may be times where you're not supposed to use the group label directly in your model because you shouldn't predict off gender, for example. But there could be a set of features that are highly correlated with that group label to the point where you basically have the same thing. And typically, the more features you have, the more effective these features will work together as a proxy. So that would be like, for men versus women, that could be, you're not allowed to use men versus women, but you're predicting based off their height, muscle mass, weight, like a whole bunch of things like that to the point where you pretty much have the gender already. And that can be desirable or undesirable. So you might want that if officially you're not allowed to use the label, but you want to use the label, like you might like kind of let that go. But if you know that you're not supposed to use the label and you actually don't want to do it, then there are methods that we'll talk about later that can remove the correlation between them so that you don't have that correlation between the feature and variable.
Okay. Wait, so
And
you'd use the proxy if you like don't have that label then?
Yeah,
too?
so the proxy kind of comes out of just the actual data itself, because if you have like a whole bunch of different data sets, so you have group 1, group 2, group 1, group 2, group 1, group 2, group 1, group 2. So amongst all of these data sets, if you have any particular one, let's say you get a point there, that doesn't tell you if that's group A or group B, like the distribution of that feature overlaps. But then let's say you get another one here, and you get another one here, and you get another one here. Looking at all of these, you can kind of be like, this is likely coming from the person on the left side group of the distribution, you know? And with the more amount of these different features with different distributions you have, the more like obvious it becomes which group it comes from, because just being that far from the like standard, like the mean with like standard deviations, the less likely that is. So yeah, it's just something that it's something that comes out of the model that you don't explicitly do. It just happens. Yeah, so then there is 5 types of biases you have to watch out for. Does anyone know them?
Selection, historical,
Yeah. Stu?
labeling,
Yeah.
it's like reporting,
Reporting, yeah.
and then
We got that one already, but that's true. And measurement. Okay. Yeah, so I'm just gonna run through them a bit. So with reporting bias, so that would be a bias in the way that people respond to a survey. So the example given in class is if you were to ask a bunch of people how much they eat fast food, you might get a reporting bias there because a lot of people might feel guilty about how much fast food they actually eat, and so they will lie on the survey.
Oh.
How
How do you deal with that?
Yeah, so that one is really hard to deal with. You typically need to know something about the actual base rate in the population. And then from that, you can try to reweight it based off what you know to be true about different people. But that one is hard to deal with.
what do you mean by base rate?
The actual true value in the population. So if you do a survey asking people how many of them eat McDonald's and like 15% of them say they do, but you actually have been like Big Brother watching them and you know that 30% of them actually do, the base rate would be 30%. So there would be a reporting bias
So
that
it's the
unpredictable.
true value. Of
Yeah, the base rate is just like the
So-
actual.
Why?
Relating that back to sufficiency, that would be the R value. Calibration.
Wouldn't that be why?
No, like,
Why is
yeah,
true
well,
value?
yeah.
Because
Okay.
that's the whole point of sufficiency or calibration is like. you're
Yeah,
gonna
if,
do your-
if you're talking about the actual risk score, yeah.
Okay.
Yeah.
Wait, how is that the risk score?
Like the true risk score. You know how it's like,
Risk was like the probability of an event like happening.
yeah,
The
that's
actual
right, yeah.
prediction.
I just had
The
Oh, this is
result.
an actual, okay, yeah.
yeah.
And all these biases come from data collection, nowhere else, correct? These are
The
five
ones
biases.
we're looking at right now are from your actual data collection, yeah. So then selection bias comes from how you choose to like get results.
Who you sample, no?
Yeah, pretty much. So an example of selection bias would be only scraping your data from Reddit posts, because old people probably don't have Reddit accounts. You know, like that's the idea behind like selection bias, is you're choosing your data in a way that will end up excluding some portions of the population. And the ways you account for that is you can obviously just select your data better, or it also talks about trying to get people to pre-register for something, so you can get a varied group of people before actually getting responses from them, and then you're like not tempted to use the data you got, I guess.
Okay.
So historical bias is bias because you're using data that was collected from the past, and like time series data, you know, there's no stationarity in it. So now in the future, things have changed. That can be due to discrimination reasons, like in the past, like maybe women were less likely to get certain promotions. So going forwards, that a model who's looking at individuals might recommend them less for promotions because they are women who historically didn't get promotions. Or if outside of that, if you're looking at like temperature data over time, if you just have a model that's trying to predict temperature from like the 1980s and you use it today, it's obviously different. And so that one's the same thing, like you can try to compensate for it by like reweighting and resampling and stuff. Yeah, a lot of them, that's the solution. So yeah, next is measurement bias. So that has to do with how you are actually recording your data. The example given in class is you have like some kind of fitness tracker and you've tuned it so it matches up with like the cadence of how your average person walks. But then if you've got like an old lady with a walker, it won't measure her the same way. It might under or overestimate her steps depending on how the algorithm works. And the way to account for that is just get more precise measurements. Like,
Do better.
and then the final one is like labeling error, and that one, or labeling bias. So that one could come from human labeled data. So, for example, if you had a person who had to label whether or not they thought somebody was attractive, that is clearly very much dependent on who the person actually is. So if you were to then get that person to label a bunch of data and train a model off of it, it could be completely irrelevant to everybody else because they have weird taste or something.
Wasn't there something to do with proxies and label bias as well?
Yes, that's true too. Yeah, good point. Yeah, for the proxies one, it's for if you have, let's say it's something you can't directly like label, like I'm just gonna use the example from the slides, it's easier. If it's something you can't exactly measure, like how much a person needs healthcare, like healthcare need in a region, you might, instead of using that, because you can't actually get that to say they have a high need or a low need, you might instead look at healthcare spending in the region, be like regions that spend more have higher healthcare demands, so they must have higher need. The problem with that is also rich areas will have higher healthcare spend. So you will have a bias there because sure, in some areas you'll have higher spend because there's actually higher need, and in other areas you have higher spend because people are going for like minor scrapes and bumps.
So it's just like more use of proxies for like a target.
Yeah,
variable?
yeah, exactly. Yeah, so if your proxy actually doesn't translate well to what you're trying to measure, and this is like a different proxy than the other proxy we were talking about. This is choosing a feature to represent something that you can't measure. It's kind of like, honestly, it's kind of like the CPS, you know, estimating the state from other shit. Like, yeah. Yeah, so that's chapter 2.
What was the 5 types again?
Selection, reporting, historical measurements, and label. Yeah. Processing chapter. Okay. So the first thing that she talks about is unconstrained machine learning. So unconstrained machine learning is literally just normal machine learning. You're not applying any constraints like we talked about from chapter 1. Fairness is a constraint you apply on models. So unconstrained machine learning just means normal machine learning. So when you have unconstrained machine learning and you have the group labels, that tends towards a certain type of fairness metric. Does anyone know what it is?
Sufficiency.
No.
Calibration.
Yeah. I mean, you you get both, so also true.
Well, isn't it the calibration like acting as like the whole entity itself as one group though? I thought that's what unconstrained.
If you have unconstrained machine learning and you also have the group labels, you get calibration by group. You need to have both.
But if you don't, you'd get like overall calibration.
If you don't, okay, we're gonna get into this.
Oh.
Yeah, that's okay. Yeah. So, like basically, with the unconstrained machine learning, like you're saying, if you have the label groups, you can get calibration by group because calibration by group is the same as just the objective of the loss function. So the loss function is trying to minimize the loss. If you also give it the group label, that's another feature it can use, so it knows to kind of use that to predict what the actual thing should be, and as the loss decreases, you'll get closer to calibration by group. If you don't give it a group label, like you're saying, if you have a bunch of those features like we looked at earlier, having a bunch of them with the same distributions, they can act as a proxy for the group, and you can still achieve calibration by group without directly giving it the group label. But then if you still are looking at that problem and instead you've removed that dependence from the features, so now the features do not actually depend, or the features do not correlate with the group label at all, you will tend towards a different fairness metric. Does anyone know what that one is?
Parity.
Sorry?
Is it not the demographic parity?
Yes, yeah. And do you want to explain why?
I have no idea.
Okay. So basically the reason why is because if you remember from earlier, so when we had our like things being separate like that, and we had that for a whole bunch of our features, we could tell like who was from who, and from that, so that's how you get the calibration parity. But if instead these distributions are identical, because there's no way you can separate them by the two groups, so group 1s looks like this, and group 2s would also be identical, because if it's not identical, then there is some correlation between the features and the group. So we're saying there's no correlation at all between the features and the group, so for each one it looks identical, it's just some distribution with a mean and a standard deviation. There's no way for the model to get information that it doesn't have as an input, so it just kind of, like there's no way for it to choose from group A or group B, so you'll end up getting the demographic parity. There's no way for it to choose against one group.
Can you quickly define demographic parity again? So the groups don't affect it?
Demographic
Basically?
parity is like the equal acceptance rates.
Equal acceptance.
So if basically if the two groups have the exact same feature distribution, there's nothing different about them, assuming you have large enough groups, like obviously like single one-off events are all random.
Yeah.
Over the long term, since there's no way you can distinguish between it, both groups will be accepted like at say like 30%. Because they can't separate between them, they look the same.
So knowing the group won't affect the prediction.
Yeah,
Okay.
yeah, because to the model, there is no difference between the groups.
Okay.
An example of that would be if we had like, we've got three features in the group label. If like first group is like, and then we've also got, and then we've got A, B, A, and then this is the prediction, or like the true value 1, 1, 1, 0, 0. If the model doesn't know the group, it can't predict, like it can't accept people unfairly, because like it just knows that 0, 1, 1 equals a 1. Like, because here the feature distribution is the same for
Okay.
the two different ones. So that's how you would get demographic parity, just with a larger amount of things. Like you would get some variance, obviously, because it's a distribution instead of the values being exact. But yeah,
So you can't have
without knowing this information, it would be demographic parity.
so you can't have demographic parity in calibration unless the base rates are exactly the same.
Yes.
Okay.
Yeah. Yeah, and that like this would be a case where the base rates are the same, so you are going to get that.
Yeah.
But yeah, if the base rates were different, then you would lose one of them because obviously it can't do both.
Right. Right.
It doesn't have the information to do both. And I mean, the other option is like the perfect classifier, where it can just perfectly, that would be one where it can perfectly classify. Does 0, 1, 1 always equals 1 and 1, 1, 0 always equals 0?
So like the perfect model scenario. I
Yeah.
guess.
Are we aiming for demographic parity when we're creating models?
It depends, that's why we have the 3 different metrics, and which one you want depends on your situation. So demographic parity is common for allocative problems where you want to give the same amount of resources to different groups. Where am I? Yeah, okay, so next is the ideas of irreducible and reducible error. So, does anyone want to give a definition?
Oh my god, there you go.
Okay. Yeah, irreducible and reducible error.
Isn't irreducible error just the error that's just always going to be there, you can't get rid of?
You can get rid of it in certain cases, but largely yes, yeah.
And then reducible is just the error you can reduce with
Yeah.
changing the
So that's an explanation. Yeah, so like I'm just going like reducible error is the error that is due to the data you have and the model itself. So that error can be reduced by, and when I say data, I mean like each entry you have in the data set, not like different features. So with reducible error, you can improve reducible error. Like say it's like not a linear problem and use linear regression. You can reduce your reducible error by choosing a more complicated model. Alternatively, if you have just like 2 or 3 data points, you can increase or decrease your reducible error by just getting more data so the model learns it better. And that differs from the irreducible error. The irreducible error to the model just looks like noise. It's the variance in the prediction that the model can't explain with any function of the features it's provided. But if some feature exists that explains some of that variance that the model can't currently explain, and you were to somehow measure that feature and give it to the model, you can reduce irreducible error. So an example of that could be if you were trying to predict precipitation and you only had temperature, there is no way to reduce the error due to other like climatic variables like wind and stuff like that if you had no way to measure the wind. Like let's say you're in some kind of box, you have no way to measure anything else. Then somebody like cuts a hole in your box so you can also measure the wind. The ability to add the wind to your model would reduce your irreducible error relative to the first situation. But in most cases, you can't reduce irreducible error because the features that contain the variance, like for the irreducible error, are just hard to measure. That's why you don't have them in the first place, kind of thing.
Okay. So the only way to reduce the irreducible is to add a feature. If
That
you
explains the variance in the target that is explained by no other function of features you have.
Okay.
Like basically, like there will be some variance in Y, right? Same as like from CPS, like the variance for like the noise and stuff like that. There will be some variance, and if there is no function of your various features that can explain this variance, that's irreducible error. However, there may exist some other function of some other feature that you don't have, I'm gonna call it Z, that explains some of that variance. So if you somehow find that feature, you can reduce irreducible error. Just usually this is something hard to measure, so you can't. Alright. Yeah, so next, there's two types of pre-processing methods that we looked at in the class. So the first one is optimal pre-processing, and optimal pre-processing is kind of weird. I don't fully get it, but like it's like you have a bunch of variables like this, and you have, or these are your like Y, your targets, and you have some set of features, and they're like 0, 0, 1, not sure, 0, 0, 1, 0, 0, 1, that goes to that one, and 1, 1, 1, 1, 1, 1. It somehow, I don't know how, but it somehow would like change these ones that are closer to being to this by being like 0.2. And maybe it makes these like 0.8. It basically looks at like how the combinations of features are like similar between them. It makes the actual prediction values like soft, so that things that are close to being like other things are closer in the way that it's actually learned.
What's this called again?
Optimal pre-processing, something like that. And the reason why this is helpful is if you have two things that are similar, like let's say it's like a student who's been from an underprivileged background, so they have like worse kind of marks, but they're still doing like pretty good, versus a student who's just like shit in the bed. Assuming shit in the bed gets like a 0, but a student who's bad, but like given other circumstances, like heading towards good, like they will get a slightly stronger thing in the training. Okay. So it will learn to recognize people who don't have like the perfect features, but are like being on par of the way as like par of the way. Okay. That's my understanding. I don't know if anyone else disagrees, but yeah.
Sorry, is that a new feature that's being added to like compensate for?
You change the target variable for training.
So the pre-processing like scales the target variable
Yeah.
based
Okay.
on the
Other features.
Okay.
Yeah.
Oh yeah.
Wouldn't that be?
Sorry.
Yeah, I don't know. Yeah, not my problem, I promise.
Wouldn't that be
It changes the
data
true
leakage?
values based on comparisons between samples.
Yeah. Like, Laura, could you agree with that? Or Edmund? Like, you guys, I feel like that's what it looks like it's doing. She's got 2 slides on it. I don't know.
Oh, 2 slides?
Yeah.
Beyond the exam.
It's like 2 slides, but it's one of the. The reason why I went over is it's the long answer. Is,
Oh, it is.
Yeah.
Oh.
It's just, and that's what I mean. Though. It's kind of cooked because it's literally 2 slides, and it's like the entire fucking long answer.
Damn. Damn. Dude, that sounds good.
She actually just wants to know more about the topic herself.
Yeah, genuinely. Get the whole thing of the topic. Okay, so the other pre-processing method is learning fair representations. So that would be if we have this is 1, 2, 3, 4, 5. We have feature 1 for and this is like 5, 1, 2, 3, whatever. So for group 1, we have this data. I'll put 1 there. And for group 2, we have this data. The issue is you can entirely predict, what group somebody is from based off one of these features here. Because you can see group A is always on odd numbers, group B is always on even numbers. And that's bad because you shouldn't know the group.
What are the numbers in this case?
Sorry?
Like, what are the numbers representing?
These are just features, sorry. So this is like your X feature and this is like your Y feature or something.
And this is called fair pre-processing.
Learning fair representations.
Oh.
Yeah.
Well, that's the long answer one, right?
Yeah, it was the long answer was you could choose between like the optimal pre-processing or learning fair representations.
Oh,
You got to choose which one you talk about.
Fair
I think this one's easier. in my opinion.
So when she put.
So wait, so what's the Okay, I guess you're about to solve the quay. Okay, yeah.
Yeah. So the way that you try to deal with the fact that there might be something that's entirely predictive of it is you will create things called prototypes. So I'm gonna put like a prototype here and like a prototype here. That was supposed to be a square. Yeah, okay. So these prototypes are, you're gonna map your features to the prototypes so that this information that was previously entirely like predictive of the feature will now not be entirely predictive, but it will still give you the same or similar information.
So it's like introducing noise in the.
Yeah, kind of, yeah. And so basically what that's going to do is you're going to learn it like same as like machine learning on a portion of your training set, and you're going to have some loss function that is a function of the distance, and it's a function of accuracy, and it's a function of your fairness constraint. So you want to map these points to these different boxes. And the way it's going to do that is it's going to like learn it the same as like normal machine learning, and it's going to try to minimize it. So it wants you to map it to boxes that are close by. So it's more likely to map this X to this box than to map it to this box. It also wants the model that like it like trains like a little model, and it wants it to still be able to accurately predict the true values. You don't want to lose information. Like if you moved all of them to this box, you're not going to be able to predict anything anymore. And then it also is trying to enforce this fairness criteria where it's like not able to predict group A or group B from the data.
Can you give an example?
This is the example now.
Wait.
Yeah, I
So
don't-
basically, it's just going to try to map each feature to a prototype feature that is similar to it, but reveals less information about it. So that's like, you're going to lose some accuracy from that. But the idea is you won't be able to predict anymore, because you see here, like X is odd, odd, and odd. So if just by doing that, your model will be able to predict like, oh, you're from group X. And like same thing, circles are always on even numbers. But if instead like you map this to here, and also you map both from both groups, you map them to the same prototypes. So like say that this one gets mapped there, this one gets mapped there, this one gets mapped there, and this one gets mapped there. All of a sudden you still have data that looks pretty similar. Like instead of having an X there and an X here, you have an X here. And a circle there, you have a circle there. So the data looks similar enough that you can still predict it and use it for like your model, but now there's no way for you to know that it came from like group 1 and group 2.
So basically, this just prevents overfitting and your model memorizing the.
It just like, it tries to remove information from the features that could let you predict what group they're from.
Oh, let you predict what group.
Does that relate to proxy? Like concept of like a proxy?
I'm all right.
like these are proxies for these, I guess.
Like, what does it mean by one group only?
That
has
might be the
features
one
from
question you
1,
never
3,
asked
and
that
5?
didn't
Like this axis here.
It's tough.
Like for
got it on
group
video
X,
too.
you see like this value for its X, oh, that's confusing. This is like variable 1. For like feature 1, if you're in the X group, you could have a value of 1, 3, or 5. It's always odd. So just by knowing the value, you automatically know it's from group X, and the circles always come from even values of variable 1.
And so the way you remove that is just.
Mapping it to something that's close by to both of them.
So what are you doing to the data in that case? Like,
You're literally like, instead of saying X equals 1, you would move in like maybe X is now, for this point, you'd say X is equal to like 2.2. You're literally changing the data by just moving it.
Why can't you just drop that entire X thing and just put them all on the Y axis and just not.
Well, because then you still don't, you don't have this information anymore. This information is still very relevant, because like, this is like variable 2, right? So what this is saying is like, when you're combining these two features, like it would be like if originally a value of 1, 1 would predict a value of like, I don't know, 2 or something like that. You want to learn a representation where instead it can know that a value of like 2 and 2.2 should still correspond to 2. Like that's what it's trying to do. But obviously you're not going to get as directly a thing because now both of these have increased. So maybe you, like when you actually train them all, you get like 2.3. And you're saying that the trade-off in accuracy is worth it because I can no longer say with absolute certainty that you came from group X.
And so that helps with which fairness?
I don't know.
Just fairness.
Yeah, it just helps with, it's just the issue is that you can predict what group something is from,
So
and you
you're
don't
adding
want
a
that.
bit of noise to prevent overfitting.
Yeah,
That's to avoid discrimination by group because it can't tell what group it's from.
yeah.
Okay.
I'm sorry, what do you pick your prototypes off of those three things, distance,
Uh,
accuracy, and fairness?
Yeah, like it's a loss function based off distance from the actual points, accuracy of your model, and whether or not the fairness constraint is made, and it will somehow pick the points. The answer is like you import like fair learning, and it does that. You know?
Do you want to take a short break, Elijah, or do you want to keep going?
Yeah, I could use some water.
All right, let's take like a 5-minute break.